Hi, everybody. I feel like I'm in the witness protection program with the light in my eyes. I don't see anything. It's supposed to be the other way around. I'm delighted that you're here. As was mentioned, I'm a founding partner at OrionX.net. We cover a lot of different topics. And if you'd like to connect dots between IoT, 5G, HPC AI, blockchain, and quantum, we can do that together. That is fundamentally what we do. But our roots are in HPC, our roots are in supercomputing, and that's really the focus of this particular talk. It's really about HPC and quantum computing. I got ChatGPT and DALL-E to produce an example of a Cray computer with quantum in the middle of it, and that's what I managed to get out of him. And the other thing that we do that you can track us is a podcast on HPC. If you go at HPC podcast with Shahin Khan and Doug Black, who's my co-host and editor-in-chief of Inside HPC. We have a weekly podcast as well as a monthly podcast that we do on that front. Basically tracking everything that's going on in the world of supercomputing, HPC AI, and I will explain how we define HPC in a bit. But that's most of our output. A lot of work that we do is in the background. So let me start with the definition as we propose for HPC. HPC is the application of mathematical modeling to natural phenomena and business processes. And that means that it is a discipline. It is not a market segment per se. And if you try to define HPC as a community, as a market, it is a performance-first market. It pursues performance almost at any cost. It is a very early adopter market. It can be early adopter because it's got a lot of technical depth. The HPC folks are technically very deep. They often know more about your machines than you do, and that's wonderful because they can add value in very significant ways. And openness really permeates the market because it's all scientific background, and collaboration and openness is very much part of the values of the community. So the discipline is HPC, and it goes from sensor to supercomputer, from edge to exascale, from device to data center. And I'll come up with a couple of other alliterations in due time. But just because it's a small system doesn't mean it's not HPC. It's not limited to supercomputing. It is really the application of mathematical modeling. And if you look at some of the advances recently on for example, RISC-V is a new instruction set architecture that's coming, and it's got a bunch of open interfaces that it does. They're putting vector instructions for sensors because you do want to do some data reduction at the point of inception where the data comes in to begin with. So that is really an example of HPC permeating across the board. The applications of HPC, you could broadly say it is simulation for prediction, usually based on a model, but oftentimes, especially with AI, it's a data-driven way of getting to those predictions, engineering design and optimization, and of course, AI. So note that with this definition, we are subordinating AI to HPC. We're saying AI is just another HPC application as being, albeit a very big killer application of HPC. And it could be bigger than the rest of the market, but still fundamentally is subordinate to HPC. In fact, if you're an organization and want to build a really good AI base immediately, your best bet is to go hire a bunch of HPC people. They have the background, the infrastructure is the same, the algorithms are the same, the discipline is the same. A lot of this stuff is really quite the same. So speaking of algorithms, matrix algebra, it turns out that there are a lot of matrix multiplies in life. Somehow nature likes matrix multiplies. Why? Because we do 3D partial differential equations, we linearize them, we apply matrix algebra, it solves it. And FFTs also, Monte Carlo also, but then a whole bunch of other things. But generally, these end up being the fundamental algorithms and disciplines that allow us to do natural discovery, really, insights and discovery. And then the formulation of these applications and these computational kernels ends up being scalar, vector, matrix, and tensor. If it's scalar, CPUs would do. If it's a vector, you've got vector instructions, vector VPUs, like the Cray supercomputers initially were actually vector supercomputers, and then they became parallel supercomputers. But CPUs now also have vector extensions. Intel chips have had AVX for a very long time. They're right there in the chip. If you can use them, it really helps quite a bit. Matrix is like GPU, but the CPUs also have matrix extensions. And if you go back in the history of HPC, as early as, I would say, like late 1980s, early 1990s, that's a couple of few decades ago, you had essentially matrix coprocessors back then to accelerate these kinds of applications. So fast forward to today with GPUs and FPGAs and such, a lot of the people in HPC have seen that movie before. And now as you go to Tensor, you've got QPUs, but of course the GPUs are also quite prominent in that world. HPC also is a great way to bridge over the chasm. So if you're a vendor, HPC is absolutely a critical market to look at because it allows you to jump right over the big chasm of a main market. Why? Because they're early adopters, right? And of course, right now, with something like quantum or with something like AI, the adoption curve is not even Gaussian. It's more of a chi-squared. It's like people are motivated to adopt. You know, many of the companies don't go through the normal checks and balances. They sort of create a separate department to go fast and break glass and adopt these things. So it's an important market to look at. If you're a vendor, you must look at HPC. That's where the money is. That's where your early customers are going to come from. The same thing happened in AI. A lot of the AI early adopter ones were like national labs and universities and HPC sites. So how do you go fast in the digital classical domain? If you divide it into a 2x2 digital, analog, classical, quantum, and you get sort of those 4 quadrants there, the digital classical world is where we've been living for the past 40, 50 years. Analog is kind of coming, but it's a kind of a pain in the neck. Quantum is now coming in both analog and digital fashion, so we are filling up that 2x2. But essentially, if you look at compute intensity and memory intensity as part of this axis on the left-hand side, and if you look at serial and parallel on the right-hand, on the bottom, so basically intensity versus concurrency, what do you do to go fast? Because that's really, at the end of the day, what a lot of the motivation is to go sell in these systems, albeit 2 other things are coming along too. So you either go through traditional optimization by just doing better coding and taking advantage of the system that you have. You use different algorithms, like approach it completely differently. And of course, with the advent of, with the renewed advent of lower precision arithmetic that's motivated by AI, you are now able to use lower precision arithmetic to accelerate parts of the simulation and get to the final answer a little bit faster. So you kind of see that too, the kind of a revisiting of error propagation for your algorithms and whether you can use lower precision or not. And then what do? You can replicate the entire system. You can replicate cores. You can replicate functional units and registers. It's fundamentally replication. You're trying to replicate something to go faster. And quantum computing is a fundamentally different way of getting that speed for certain applications. And that gives you clusters, multi-core, vector, in-memory, chiplets, etc. The current trends in HPC, what's hot right now, is AI. You want to enable AI, and you want to use AI. Where do you use AI? In mixed precision, as we mentioned. In code for accelerators, like can I use AI to help me code for accelerators? Because that's like non-trivial. To help me optimize the apps, because it can find optimization paths that I couldn't get otherwise. And to manage very complex systems, right? Let me go to the other end of this slide first, and that's sustainability. So if you were at the supercomputing conference a few weeks ago in Atlanta, liquid cooling was front and center. Why? Because the GPUs are really hot. And a typical data center in the old days was like 10 kilowatts per rack. The HPC sites were 20 kilowatts per rack because they were really dense. Nowadays, you're lucky if you can kind of go below 40 or 50 kilowatts per rack, right? And if you want to air cool, there's no way you could do more than 100 kilowatts per rack. The latest rack with the latest GPUs is 125 kilowatts per rack. The roadmap shows 300 going to 400, going to 600 kilowatts per rack. That means that if you're a typical data center and you put one of these racks in, you have to remove a half a dozen to create enough cooling capacity for it to be run. So Cooling and power are really number one. You need to source power. You may have read that Microsoft cut a deal with 3 Mile Island to revive that, that nuclear power plant and they're going to build a data center right next to it. So you need power availability and you need power transmission. Los Alamos National Lab needed more power. The power is available, but it has to go through some protected land. So there's a whole, political and legal issue to kind of get there. So sourcing power is difficult. Transmitting power is difficult. Cooling the system is difficult. Transmitting the heat out of the building is difficult. It's not enough to just take it out of the rack. You have to take it out of the building. You have to take it somewhere else. So that is absolutely front and center in the supercomputing world. And it is really interesting because now, how do you cool it? Air cool it, liquid cool it, is it water, is it dielectric? Do I need filters? Do I need to, does it corrode? Does it, react over time? So all of those complexities are like coming in a big way. And then in the middle, you have to look at new technologies, accelerators, quantum computing is one of them. They're going to go fast no matter how they can, if they can get it, they will go do it. Edge devices are now becoming also mini supercomputers themselves. Your instruments, like if you have a gas chromatography, or if you're Argonne National Lab and you have the biggest photon source in on the planet, or if you're Los Alamos and you've got something like those instruments are themselves becoming supercomputers. If you're CERN and you've got a Large Hadron Collider, that is itself becoming a mini supercomputer. So how do I really integrate those? And then those are, of course, outside of the campus. So multiple campuses might have expertise that you want to connect. So that is leading to federated supercomputing, and there's a whole activity going on to provide the software for that. And then all of this leads to what I call up there IHA's integrated heterogeneous supercomputing. The concept of integrated heterogeneous processing is not new in supercomputing. Again, it was something that was bandied about back in the 90s, 1990s that is. And it's coming back because now you really are trying to integrate all these systems into one. And HPC needs quantum computing. Right? The top part is kind of what we talked about before. But HPC grand challenge applications carry on. These are grand challenges. They're hard to do. Climate modeling, nuclear stockpile management. That's what feeds a lot of the DOE, Department of Energy, activities. Precision medicine, cognitive science, national security, condensed matter, new materials, some of the stuff that we talk about in quantum computing as well. These are all really big problems. They're never going to go away. And it's just like, the more precision you give them, the better they'll take it. But the quantum advantage, that really might just be my biggest point in this presentation, is that quantum advantage isn't just speed in this market. It is also accuracy, and it is also energy. If a quantum computer can be twice as slow, but 100 times more energy efficient, they'll take it. Because the energy problem is really, really a big problem, and it's not getting solved anytime soon. There's like neuromorphic chips that are coming, but then that's just for AI. It's, you're not going to go do science with it. So that, it is important to keep those 3 prongs in mind, that quantum computing isn't just for speed. When you say quantum advantage, it could be energy advantage. It could be accuracy advantage. And what are the expected applications in HPC? Obviously, quantum chemistry, quantum physics, because, well, it's already quantum, but also optimization. But what was new to me, and we talked about it at SC24, was parameter optimization. So they're now using quantum computing and AI to do optimization of the input deck to the system. And then, of course, QML we've talked about, and cybersecurity we've talked about. Cybersecurity has always baffled me because it's on quantum. It's like what you're afraid of. You're not using quantum computing to protect yourself. You're afraid of somebody else using it to attack you. But when every time we announce something like Google did this week, the whole cryptocurrency world goes up in arms. It's like, is this the end of Bitcoin? And you have to calm them down and say, no, there's still kind of a road to shore presentation that David Shaw gave yesterday that tempers the whole thing. It's you got a little bit more time. But the whole idea of quantum safe cryptography has been making its way, as you all know, through the regulatory system and different directives. So it's kind of happening. And NIST now has at least 3 algorithms that are getting vetted and getting proven over time. And some HPC quantum examples, as Bob Sorensen mentioned in a separate talk earlier, that Euro HPC in Europe is really where a lot of the action is. They are funding a lot of systems in Europe, and that's definitely something to track. But on the left-hand side, you see vendors, and what do they do? Fujitsu has a hybrid quantum platform that can simulate up to 64-qubit systems. They have a 64-bit qubit system. They can simulate up to 40. They have also a digital annealer chip, so they kind of have a pretty comprehensive coverage, if you ask me, and a very nice system. Eviden, the French company that was a spin-out of Atos, have an environment called Captiva. It is also quite well done, one of the best out there that is really allows you to go simulate. And then also, of course, NVIDIA with Q Quantum and other libraries, and they just had a new release of it a couple of weeks ago. On the user front, U.S. government, we don't know as much about China. It's kind of all my bottom. There was just some news a couple of weeks ago that the Chinese Academy of Sciences and one of the telecommunication companies has a 504 superconducting qubit system that is based on their Shahin chip, and it's available through a cloud, albeit the rumor initially was that accessing it through the cloud was a pain in the neck. But the news article said that it's accessible by like 40, 50 countries. The universities in the US, it's really national labs. Oak Ridge, Argonne, Lawrence Berkeley, Sandia all have test beds for quantum computing, and seems like some kind of a coordination is happening for them to see who gets what. US cloud providers are obviously having an increasing emphasis on HPC. AWS is doing like a whole zone with DGXs from NVIDIA. They're also doing their own AI chip. They're all kind of coming up with InfiniBand networking, so they're trying to kind of cater to HPC. And of course, university sites. There are a lot of university sites that are very strong in quantum computing, but they don't have a really big supercomputer on site. Like Caltech is an example of that. Berkeley is an example. It's not on site. It's like across the street as at Lawrence Livermore, Berkeley. And then there are those that actually do have on site. And those also invariably are getting more interactions with quantum computing. In the European world, LRZ, Leibniz, and Jülich are probably the two most notable ones. But there's also GenC and CAE in France, Ceneca in Italy, BSC in Spain, Poznan in Poland, et cetera, and ETH in Zurich that also has a non-trivial cluster on site for supercomputing. And RIKEN was mentioned earlier, the Japanese supercomputer that is also the home of Fugaku, which was the #1 supercomputer on the planet some years ago, and it is just a gorgeous, beautiful machine. If you're going to build a supercomputer, build it like that. It is just fabulous. It's only bested by what it replaced, which was the K computer, which was also a beautiful machine. So those guys know how to build really beautiful systems and very efficient systems. Not just, one of the big benchmarks in the supercomputing world is LINPACK, is high performance LINPACK. And that sort of represents the best you can do, really. It's like the practical peak performance you have a shot at getting. There's another benchmark called conjugate gradient, HPCG, and that is representing sort of the minimum performance. Like you look at a giant supercomputer, and it could get maybe 80%, 90% of its peak performance on LINPACK, and then it gets like 1% on GCHQ, on HPCG, HPCG. So Fugaku gets 3%. So it's like literally 2-3 times better than the other guys. All right, and then what are the problems to be solved? In this market, the problems to be solved are exactly the same as they were last year this time. The infrastructure, you have to map the algorithm to quantum operations. You have to map the algorithm to the specific hardware. You have to integrate with supercomputing applications. I'm delighted to see more project and more research on input-output and coding and feeding data into quantum computers. I've been kind of waving the flag for a long time that that's going to be a big problem. And it's finally getting attention. I think that'll be critical and needs to be done. The algorithms, the accelerator model is well understood in the HPC world. They use it. Hardware availability is really important, and it's not always there. Integration again, and round-trip latency, that goes right back to the I/O. And then the workforce training, access, delivered performance, and But this is really might be another point, is that we must move past quantum inspired, and we need to get to quantum real. If you don't do that, GPUs are going to make all the money. Quantum computing needs to actually provide some kind of an advantage. And again, my vote is look at energy advantage as well as speed advantage. So that's really kind of my conclusion. We expect HPC to be the first and the main market for quantum computing. Why? Because it has an early adopter mindset. They're brave. They're not afraid of new technology. They have suitable applications. They know how to get them funded. They have a very technical user base that can actually solve problems and work with you to do this. And they see it as the next step in supercomputing. So they're kind of motivated to engage with you. All right, so with that, I will pause. I will do another advertisement for my famous podcast as our expanding media empire touches everyone. And I'm delighted that you're here again. Thank you very much.